crucial question is, what can statistical optics offer quantum optics? In this lecture, I try to actually come up with some explanation and also give you an overview of how statistical optics is important to understand some fundamental concepts in quantum optics, and it can be extrapolated to even quantum photonics and spectroscopy of quantum objects. But to begin with, one of the crucial aspects to realize is that statistical optics is kind of a preamble to the quantum nature of light. So what do you mean by quantum nature of light? Specifically, majority of the physics education starts with classical mechanics and builds up all the other interesting aspects of mechanics as one really goes deep into the concept of statistical physics and also basic quantum physics. The important aspect here to appreciate is that light historically has been not a very easy particle to be categorized, and it also has very unique characteristics. It also comes with a very fascinating distribution function, etc. But the motivation here is to capture the statistical nature of light sources and also connect them to quantum optical phenomena. In that sense, one can understand the nature of light from a quantum mechanics viewpoint via statistical optics. So that is one of the main goals of these lectures. There are two important sources I have consulted, and I have been reading this over the years, and I found it very useful, intuitive, and also a good read, so to speak. One is the Fundamentals of Photonics by Sala and Tech, and the other one is Optical Coherence and Quantum Optics by Leonard Mandel and Emil Wolf. All the four gentlemen worked in the area of quantum mechanics, quantum optics, and quantum photonics, especially Sala and Techie. They have some fascinating aspects to reveal, and their research papers are equally interesting. And the book and the discussion in the book is founded on many interesting concepts that they have built and studied over the years. So the motivation here is to utilize their knowledge and also add some historical and, in certain cases, philosophical questions related to quantum phenomena. And we will take it up as and when we progress during this particular lecture. First aspect is to look at the statistical optics as a study of random light. Particularly, the randomness is inherent to majority of the light sources what we study. They have unpredictable fluctuations, and this fluctuation can be due to the light source itself, or it can be due to the medium in which the light is propagating. And this is an important concept to appreciate, because the fluctuation's origin can be both the source of the light and the medium itself, and this creates some very interesting categorization, and also it reveals something both of the medium and of the light source, because the fluctuations have some very critical information, so to speak. Now, if you consider the case of natural light sources, it can also be considered as a superposition of emission from atoms, or it can be molecules, or it can be any kind of light source which gives rise to some very interesting characteristic signature in terms of the emission process. Scattering of light also leads to randomness in intensity, phase, and if the scattering happens to be inelastic in nature, it can also lead to randomness in frequency, which takes the domain of this interaction not only from spatial, temporal, but also into the spectral domain. And that's one of the unique characteristics of studying such kind of systems. The study of randomness of light also is the foundation on which the theory of optical coherence is laid. And the two books I referred to earlier does build the theory of optical coherence from elaborate study of randomness in the fluctuation, mainly because of the fact that the light source what you're considering itself has some very interesting characteristics, which has some very deep insight into the kind of interaction what we can obtain. Now let's look at the light sources themselves. One of the important categorization what you can have is the division between coherent source and the random source. What you're seeing here is also the monochromatic coherent source. So if you take the time dependence of such kind of a source, you would see a uniformly spaced oscillatory function in terms of intensity, or it can be also some specific parameter of the monochromatic coherent source, where the distribution of electric field can also be studied in that way. Whereas in the random light source, the field itself actually has random fluctuations, and this gets reflected in the wavefronts of the respective light sources. If you look at the light source wavefront, the monochromatic source has a very uniform spacing as the wave evolves across space in a particular direction. It would be uniform and have equal spacing between the two phase fronts. Whereas for the random source, you would see there is a fluctuation in the wavefront, which itself brings some unique characteristic and has deep implication in understanding randomness. The question now is how can we extract from these kind of fluctuations of random optical wave some meaningful measures that characterize it and distinguish it from other random waves. What do I mean? If you have, let's say, a variety of random sources, how will you be able to distinguish between one random source and the other random source? That's a crucial question to address, because we are able to discriminate between, let's say, a coherent source and a random source. But it is equally important for us to realize how to distinguish between a variety of random sources. And the random fluctuation of the field as a function of time can take any kind of arbitrary nature of waveforms, and therefore it is necessary for us to study it, and statistics plays a critical role in such kind of system. What is of interest for us is to go from a qualitative observation to a quantitative measure in such kind of fluctuating signatures. In there, the statistical averaging leads us to non-random measures, which are equally important for us to quantify this whole process. And the random function satisfies certain laws, and those laws are important for us to appreciate. And statistical averages also satisfies certain laws. And what are those laws and what are those functions is something of interest to this particular discussion. Essentially, the measures also give rise to classification of light. One can talk about coherent, incoherent, and partially coherent sources by looking at these measures. That is one of the important consequences of utilizing these kind of statistical measures, because you would be able to now discriminate between coherent source, incoherent source, and partially coherent source by looking at certain aspects of the measure. So, what will we learn during this particular discussion is the question. We will look at two statistical averages. We will look at optical intensity, a kind of a definition of optical intensity. One of the crucial concepts which we are going to learn is about mutual coherence function, and this function has very handy utility in variety of problems. We will also look at the distinction between temporal and spatial coherence of light, and the connection between temporal coherence and monochromaticity, and it's a very fascinating connection which is important for us to realize. And a kind of a definition of partially coherent light, which gives rise to spatial coherence and temporal coherence. And when you have such kind of coherent properties, the spatial and the temporal coherence need not go hand in hand. And this is one of the very fascinating aspects of partially coherent light, because you can have something spatially coherent, but it need not be temporally coherent, and vice versa. And this is one of the unique characteristics. Why is that so? We're going to look at it as we go ahead in this series of lectures. So another important reason why we are looking at these kind of interactions is to come up with a law of interference of random light. And the kind of interference formula what you have traditionally studied in physics actually can be revisited and recast in the language of statistical fluctuation. And one of the critical goals in this particular series of lectures is to come up with this law of interference of random light. And why is this necessary? It is necessary because it is one of the elegant ways to approach statistical problems, but also quantum mechanical problems. You would have all heard about Young's double slit experiment and also its utility in quantum mechanics and quantum optics. What is that connection? Why is that so important? This is the reason. The interference phenomena is at the heart of the statistical nature of the fluctuations, and how does it actually lead to certain consequences is one of the crucial elements behind this discussion. Now let's look at the statistical properties of random light. We're going to get started with this so-called wave function, where I am associating it with a small u, which is a function of r comma t, where r is the spatial coordinate, a generalized spatial coordinate, and t is the time coordinate. This particular wave function is essentially representing the real part of the amplitude function capital U, which is again a function of the spatial and temporal coordinates. This particular u of r exponential j omega t is representing some kind of a monochromatic light. It is kind of a plane wave, so to speak. But for a random light, both functions, the small u r, which is a function of r and t, and the capital U are essentially random. This is one of the crucial aspect I want to emphasize. Unlike the conventional light sources, for the random light, both the small u and the capital U are random in nature. And this is a crucial aspect which you have to keep in your mind while studying the statistical properties of random light. And these parameters u of r, capital U and small u are characterized by a number of statistical averages, and those averages are of interest. And one of the important averages what you're going to study is the optical intensity. In the context of the optical intensity, what is the definition? Let's look at it. The intensity, which is again a function of the spatial and temporal coordinates, is modulo capital U r comma t, and this is square of that modulo function. So the monochromatic coherent light essentially takes this particular form, what you are seeing on the screen. For a random light, intensity has to be defined by averages, as the wave function is a random function of both space and time. And this is a crucial discussion which I want to extrapolate further, is that the optical intensity of the random light has to be considered from the averages what you extract from the wave function what we are defining. Here when we call something as wave function and the parameter small u, it can be a generalized parameter for an electric field or a magnetic field, so to speak. And in most of the books, the small u is used as a generalized kind of a function because it can either represent the electric or the magnetic field. Which means now we'll go to a particular definition of the average intensity of the random light, and that particular average intensity is essentially given by this equation, where you will observe, unlike the monochromatic coherent light, you now have a very crucial difference. And one of the difference you can see here is that you have this particular bracket function which is associated with the averaging of this modulo function. And therefore this becomes a crucial aspect of the discussion in understanding the intensity, which is now a function of both space and time. Now what does this mean? Let's try to understand this further. There are a few points which I would want to emphasize, and also I'll elaborate with some specific figures. First point is that wave is produced repeatedly under the same condition, which means that you essentially are getting some particular emission of light from a particular source. The second point is that each trail leads to a different wave function, and this is the inherent randomness of the light source what we are considering. And the third aspect is that the average intensity at each point and each particular time is determined by this particular function. So you will have to consider each and every point and each and every period or each and every instant of time to measure these kind of intensities. So let me illustrate this with an example. For a random light source, the average intensity may be time independent or may be a function of time itself. What does that mean? Look at this interesting illustration where on the first row what you're seeing is essentially the fluctuation in the signals, and plotted here is the modulo u square. And in context of the modulo u square, this particular source what you're seeing has this huge amount of fluctuation. Whereas if you take the average of that particular intensity, because you remember we have to now take an average of that particular intensity to get the actual intensity by definition, this will give you a flat line. And such kind of a source is usually called as a stationary source. And this is an important point what I want to emphasize here. Whereas if you take, let's say, this kind of source, in spite of the fact that you have now this modulo square of u, you still have these fluctuations, but there is an overriding kind of shoulder peak which is part of this particular spectral feature. And if you take the average of that particular function, you will see that there is now a very nice fluctuation in the intensity as a function of time. Such kind of light source is usually called as non-stationary light source, and this is a crucial difference between the stationary source. Please look at this carefully, because in spite of the fact that there is large fluctuation, the averaging out smoothens it out, which means that the intensity essentially now takes a very flat kind of a behavior. Whereas in the case, if the function actually is non-stationary, which means the light source itself is non-stationary, you would be averaging out the noise, but the spectral feature of this particular function still remains a function of time. So it's not a flat kind of a behavior as you see in the stationary source. Now, there are realistic examples for this. For example, an incandescent lamp essentially behaves like a stationary source, although there will be a fluctuation in the intensity, but the overall average intensity would be the same for a longer duration. Whereas if you take an electric pulse from an electronic source or any kind of source, this is the kind of behavior you should expect for such kind of systems. And this forms a very interesting distinction between these two kind of waveforms. For the stationary case, please remember that the averaging over many realizations is not necessary for the reason what is illustrated in this particular diagram. Whereas if you take, let's say, the generalized function of intensity, then you have to take this capital T, which is the total time period which is tending to infinity, because you are now considering it over a large time scale. Then it can now be associated with an integral minus t to plus t, and this modulo u square dt has to be taken average with respect to minus t to plus t. And this is an important kind of distinction, and this is kind of a generalized definition of intensity which we'll have to keep in our mind. Let me introduce you to another very fascinating concept, which is called as an autocorrelation function. What is it? Autocorrelation function describes the extent to which the wave function fluctuates in unison at two instances of time separated by a given time delay. Okay, so let me tell this very carefully. For a given time delay, you would ask, how does the wave function fluctuate in unison? Okay, let me illustrate with an example. If you take this particular light source, let's say it is an arbitrarily fluctuating light source as a function of time, and this particular light source has large variation in its field. So the information what you get out of this is that it establishes this particular function, autocorrelation function, establishes the time scale of the process that underlies the generation of this particular wave function, which means that in order to understand whether this same wave function what you're considering how does it correlate to itself at a different instant of time is what is measured in the autocorrelation function. So let's put that in a slightly more stronger footing and try to understand how does it connect to some important measures. One of the important measures which is connected to the autocorrelation function is so-called temporal coherence function. So let's consider this temporal coherence function with an illustration. Consider the autocorrelation function of a stationary random wave. Its autocorrelated function can be defined as following. You essentially have this integral which is now capital G, which is a function of the tau, where tau is that particular instant what you are measuring between two specific instances for the same light source. And the important aspect here is that now you take the complex conjugate u star and you time transpose the same function u with respect to time t plus tau dt, and the integral runs from minus t to plus t. This is the period what you are considering for this integral to be evaluated. The other important aspect to note here is that the limit t tends to infinity, because you are essentially interested in how this light source behaves over a very long duration. And of course, the 1 by 2t essentially takes care of the normalization with respect to time. Now, the crucial aspect is that this is generally represented by this capital G as a function of tau, and it now is represented by this bracket function u star with the complex conjugate of the wave function which we have already mentioned, and now transposed in time t plus tau, and the bracket closes. This is usually the important temporal coherence function, which is something which you should be aware of, and it is an important measure because it tells you how that particular source behaves at a time t and also at the time t plus tau, and how does this actually relate to each other is what is the question addressed in this particular function. Now, what value this function can take and what does this mean? It's an important question for somebody to address in a elaborate detail. But what is crucial for us is to look at this function in a normalized way. You will take some specific aspects of this coherence function and you will now define something called as degree of temporal coherence. First, let's normalize this autocorrelation function. What do you mean by normalization? In the normalization, the crucial difference is this: there is a denominator to this function, and this is one of the most important autocorrelation functions you will come across. This is extensively used in literature. It actually is given by small g as a function of tau, where tau is this small kind of time gap what you're considering between the light sources. You also have this g of tau normalized to g of 0. What do you mean by 0? Here you can observe that the time goes from t to t plus tau, whereas this is with respect to the same time instance. It's a conjugate, so essentially it is at the 0 time delay, and this normalizes this temporal coherence function, and this normalized autocorrelation function is also called as complex degree of temporal coherence. And degree of temporal coherence is now measured by this particular measure. And you can see that this particular function can take a limit value all the way from 0 to 1. It would be an arbitrary value between these two numbers. If there is hardly any correlation between the time t and t plus tau, if there is zero correlation, then you will end up with 0. If there is a perfect correlation, then you will end up with 1 value. But for all the values in between, you will have something between 0 and 1. And that's the meaning of this particular degree of temporal coherence, which means that it will tell you to what degree the temporal coherence is preserved in such kind of a system as it's evolving with respect to time. Now, this is a measure of the degree of correlation, so to speak, and it actually has a very fascinating connection to something called as coherence time. Okay. Now, what is coherence time? Coherence time essentially is taking this particular function and monotonically decreasing with the time delay, which means that you will now be able to ask, if you have this kind of an arbitrary fluctuating function, what is this particular time delay between t and the t plus tau, that is the tau c, which is the specific time delay, which will preserve the coherence between this particular time delay. In other words, the value tau c is a specific value at which the small g, this particular small g, drops to a value of 1 by e of the maximum value, and that is described as the coherence time. Okay, what is coherence time? Coherence time is essentially that particular time for which this small g value drops by a value of 1 by e of the maximum value, and therefore it gives us a measure of the preservation of the coherence, in this particular case the temporal coherence for this particular system. Importantly, it also can serve as a measure of memory in terms of the time of fluctuation, and this is an important element also in the context of understanding how system evolves, because the system remembers its trajectory, so to speak, in such kind of a system, in such kind of a scenario. Going forward, now you can have a very interesting way of plotting this particular function. We now have this small u of t, and there is now a tau c associated with this, and you will now be able to plot the modulo g, because the modulo g actually is now a function, because it now is everything above 0. So what you see here is, if you plot the modulo g, you get this very fascinating kind of a peak, which is plotted as a function of the tau, and the full width at half maxima, where the value of the g, which is the maximum, drops by 1 by e, is the tau c value. This is another way of looking at the coherence, the specific function tau c, which we have already defined. Now you can see that here is where you will be able to discriminate between two random light sources. This tau c is different from this tau c. Although both the sources are random in nature, you now have a handle over how these two systems actually are different from each other by merely plotting this g tau, modulo g tau, because one of them actually has a smaller tau c, whereas the other one has a larger tau c. So this gives you a very important hold over the discrimination between the two random fluctuating light sources. So put another way, for values tau less than tau c, the fluctuations are strongly correlated, and for values of tau greater than tau c, they are weakly correlated. So how do you call a specific system to be correlated? Is through this particular function tau c, and this tau c would be able to help you to distinguish between whether the source is weakly correlated or a strongly correlated system, and this is an important measure, and it has been extensively used not only in optics, in various different areas of physics too. So there is a relationship also which you can now look at it. Tau c is now essentially a minus infinity to plus infinity. This modulo g tau whole squared d tau is what gives you this particular function. So this is a mathematical function which can be extracted by taking the integral from minus infinity to plus infinity of this function g tau, what we have already defined. So this also segues us to another important concept called as coherence length. Now coherence length actually has a very interesting characteristic. It is, let's say, some specific length associated with the coherence time. Okay, so the relevant time scale for us to cover this length L within the tau c is what is associated with the coherence length. So if the light will be perfectly coherent if the length small l is such that it is less than the product of the c times tau c. So you can see it is associated with the tau c. Tau c is the fundamental parameter in this case. It is the temporal parameter which actually is associated with the coherence time, and the velocity of light times the coherence time gives you the coherence length. So this is an important measure again going forward. It tells you that what is the distance you can cover for a particular source without losing correlation, and that's an important part of looking at the random sources. So the random source evolves over space and time, and the time is now associated with the tau c, and the length is associated with L. So therefore you now have a temporal parameter and a spatial parameter, and the spatial parameter is essentially given by the so-called coherence length. So the LC essentially is equal to C times tau c, and this is the formal definition of the coherence length. Please remember, you need to have this important parameter tau c to actually figure out the LC. But in measurements, it's the other way around. You would be able to now measure what is the distance which the source covers before it loses its coherent property. In fact, in laser sources and all, it is the coherence length which is easy to measure. Please remember, it's very difficult to measure very small time scales, whereas it is relatively easier to measure small length scales, and therefore this gives us a very important intuition into the fluctuation of the sources. Another word on spectral properties. This is not something crucial, at least for the course I am teaching, but you should be aware of this part, which is the power spectral density. So you can now define a spectral function in terms of the intensity, and the intensity essentially is given by this integral 0 to infinity, some particular parameter called as S of nu. Nu is the frequency. Please remember, until now we had not introduced this nu, which is the frequency domain, and d nu happens to be the small kind of this small frequency window what we are considering. This also is associated with this specific parameter where the limit t tends to infinity 1 by t is now defined by this time averaged or this frequency averaged modulus function of Vt, which is also called as power spectral density. So intensity can now be defined by the so-called power spectral density, and that particular energy spectral density connection to power spectral density is given by this formula. You now have something called as energy spectral density, and that energy spectral density is connected to the power spectral density, and the power spectral density is connected to the intensity. So this is just giving you another definition of intensity from a spectral function viewpoint. This is just an aside from the conventional definition what we have been using. Now you may ask, where does this energy spectral density come from? Well, the energy spectral density is now connected to a Fourier transform. As you can already see, this is associated with this function u. If you remember the u which we already defined, that particular u is now exponential. This is the complex number I, but represented as j in this particular case, 2 pi nu t dt, and this function goes from minus t by 2 to plus t by 2. So this is an important connection and also an important definition of intensity, which is defined through the spectral function or the spectral density. The intensity is now dependent on this particular function S, which is the power spectral density, and the power spectral density is connected to the energy density. Energy density is further connected to the amplitude. So in another kind of way, you can also connect this particular S what we have defined and connect that to the capital G, which we also defined earlier, which makes an important connection. So you can see that the intensity and the correlation function what we defined also has a connection. So this connection comes via this power spectral density, and the Fourier transform of the autocorrelation function essentially is the power spectral density. So this is another way of defining the intensity. That is what you have to keep in your mind, and that plays a critical role while understanding spectral features of a particular light source, and this is in the frequency domain. So this particular relation also has a formal name. It's called as Wiener-Kitchen theorem, and it has a very interesting mathematical physics kind of connection. I'm not going to go into this discussion, but you can look up the books what I have suggested, and it has some interesting discussion too. Okay, now if you look at this spectral width, you can also look at this so-called S nu, which is the energy density what I defined. This is in the temporal domain, and this is the Fourier transform of that. And the crucial element between this, the Fourier transforms is very evident here. Thinner the tau c, broader is the delta nu, and broader is the tau c, thinner is the delta nu. And therefore, for a given particular source which actually has a defined tau c, you still have this very kind of well-defined g of tau modulo, and you take the Fourier transform of that, you would see that the spectral energy density actually changes. So this gives us also a very interesting connection between the temporal aspect of light, the randomness, the correlation function. It's a modulo G is essentially the normalized correlation function, and this is the energy density function, and therefore you would be able to have this very interesting connection. Shorter the tau c, larger will be the full width at half maxima in the spectral function, which makes a very interesting connection, which means that the broad spectrum has broad spectral width and short coherence time, and sharp spectrum, for example, sharp spectrum has narrow spectral width, right? It has a narrow spectral width, for example, and a long coherence time. So this is a long coherence time. So therefore, this gives us a distinction and also connection between the width of the spectrum and the coherence time. So this is also very interestingly connected to the energy time uncertainty in an interesting way, which we will revisit at some point of time. So how do you create a light source with a short coherence time? That is an interesting challenge, as you can see, because if you can get a very short coherence time source, you will get a very broad spectral feature, and vice versa. And therefore, you can start engineering this kind of system by playing around with the spectral width and the coherence time respectively. Now, this is also connected to the realistic light sources. For example, you can start studying spectral density functions for variety of geometries. For example, you take a rectangular kind of spectral density, Lorentzian, Gaussian, and each and every aspects of such kind of systems have their own spectral width. For example, for rectangular kind of system, if you have a rectangular spectral function, the spectral width essentially is given by 1 by tau c. For a Lorentzian, it's given by 1 by pi tau c, and for a Gaussian function, it is 0.66 divided by tau c. Now, the crucial aspect and why we are discussing this whole thing is this. You now have sources of light, for example, sunlight, LED, sodium lamp, helium neon source, and a single mode helium neon source. You can now measure this delta nu by doing a spectral measurement. So you can see that it goes from 10 to the 14 up to 10 to the 6. And you can now compute for this particular delta nu what is the tau c value, which is essentially the inverse of this. And this is what we learn. This is a very fascinating kind of a table because you can see that filtered sunlight has extremely small tau c value, as small as 2.67 femtoseconds. The coherence time of a natural source like sunlight is extremely small, and its coherent length is 800 nanometer. What does that mean? As you cross this limit of 800 nanometer, the filtered sunlight loses its coherence property. This is one of the crucial ways to distinguish between coherent, partially coherent, and fully coherent source. Take the example of light emitting diodes. It would actually have 67 femtoseconds, 20 microns LC. But as you go to laser sources, for example, single mode helium neon laser, you can see that the tau c value is 1 microsecond. Contrast that to 2.67 femtosecond. It's a very large difference. And the coherence length for what it was for sunlight was 800 nanometer has now come to 300 meters. You can just look at this. This is a 9 orders of magnitude shift. For filtered sunlight, it actually loses its coherence property very quickly. Whereas a single mode helium neon laser, which can traverse over a long distance, actually can preserve its coherence length up to the length of 300 meters. And this is one of the remarkable characteristics of the laser source. And this is what really is the coherence of a laser. This is exactly what you mean by coherence, because it actually has a very large coherence length, because it can traverse over a long distance and yet preserve its coherence property. So what we have learned until now is the temporal coherence function, which is capital G of tau, We also looked at the degree of temporal coherence function, which essentially is the normalized function of this particular function. We also learnt about the coherence time, which is given by this integral minus infinity to plus infinity modulo g tau squared d tau, and the coherence length LC, which is equal to c times tau c. And you also learnt a little bit about spectral density function, which has a direct connection to this capital G. And finally, the spectral width itself actually has some connection to the coherence time and coherence length. So this gives you a very kind of a nice overview of how things are with respect to statistical fluctuation. And what I have discussed in this lecture is mainly in the terms of the temporal coherence function. And this is the fundamental concept, as I have been telling in the class. The temporal coherence function is very critical for us to understand various properties. And going forward in the next lecture, I'm going to talk a little bit more about the spatial coherence function, which also brings in its own complications and fascinating properties. So until then, do have a look at the sources, what I have already shared. You'll be able to learn a lot studying them in detail.